In this video, we compare and contrast two different types of idealized atmosphere, a barotropic atmosphere and a baroclinic atmosphere. An idealized atmosphere where surfaces of constant pressure and density, or specific volume, coincide is referred to as barotropic. And using the ideal gas law, P alpha equals RdTV is constant, shows us that virtual temperature surfaces also coincide with pressure surfaces. That is, virtual temperature is constant on a constant pressure surface. And then it's not too difficult to show that in a barotropic atmosphere, P alpha rho TV and phi, assuming hydrostatic equilibrium, all coincide. Some areas of the tropics may be characterized by a barotropic atmosphere. We can see that by looking at the NCEP reanalysis of the January thickness field from 30 south to 30 north. And you can see that large areas of the tropics are characterized by weak gradients in the thickness, which means weak gradients in virtual temperature and pressure. An exception is over northwestern Australia, where there's a maximum in surface heating associated with the heat low. Otherwise, the gradients in thickness are typically weak. Compare that to the mid-latitudes, and in particular the winter hemisphere, which is the northern hemisphere for this diagram, with stronger thickness gradients, there are stronger temperature gradients, etc. And this is referred to as baroclinic. On a baroclinic, or in a baroclinic atmosphere, surfaces of constant density are sloped relative to surfaces of constant pressure. And we see that that's often the case in the mid-latitudes. This compares, if you remember, to the barotropic atmosphere, where density and pressure surfaces coincide. Strong baroclinic zones are normally associated with active mid-latitude frontal systems. And these baroclinic systems owe their existence to something known as baroclinic instability, which is where if you have westerly flow increasing with height in thermal wind balance and a north-south temperature gradient, this is unstable for certain small perturbations. These grow into large perturbations, which gives you the alternating high and low pressure systems you see in the mid-lats. In their formative stages and decay stages, baroclinic systems display tilting with height, and you'll explore all of this more in mid-latitude. Here's an example illustrating baroclinicity. The solid lines are mean sea level pressure lines, and the dashed lines represent thickness. We refer to the region of strong thickness gradient as a barocline, and it indicates strong differential temperature advection and is associated with cloud bands. Well, why is that the case? Well, the mean virtual temperature is indicated by the thickness pattern has a strong gradient, and we can see that the thickness lines are at large angles to the isobars. So what does all of this mean? Well, the baroclinic zones are indicated by sharp virtual temperature or thickness gradients. And in this particular example, we can see that the cold air lags the surface front. So that, in other words, the thickness trough, which is associated with the axis of lowest values of virtual temperature, or the coldest air, lags the surface front. We can relate the thickness pattern, as we've already noted, to the mean virtual temperature for the layer, which via the thermal wind we can relate to the mean flow in the 1000 to 500 hectopascal layer. And so you can see that the mean flow associated aloft of the front is northwesterly. Ahead of the cold front, Adelaide, for example, would be experiencing warm air advection at the surface and a west to northwesterly thermal wind aloft, as indicated by the thickness pattern. Immediately behind the surface cold front in the Southern Ocean, the mean thermal wind aloft is northwesterly, and it's quite strong. So how does this relate to cloud bands? Well, here's two thickness patterns. On the left we have a very sharp thickness gradient and a very sharp thickness trough, and on the right a weaker thickness gradient and a weaker thickness trough. So with a strong thickness gradient on the left, that means that the thermal wind is strong. And there's a good poleward component to the thermal wind, that is a good north-south component to it. And this is associated with broad-scale uplift, stretching and lifting, producing cloud band. So the formation of mid-level ACAS. On the right-hand side, there's a weaker thickness gradient, which produces a weaker thermal wind, and there's less of a north-south component, which is going to produce less stretching and lifting and a weaker cloud band.